All right, welcome to CS4510. The topic of today is on regular expressions. 3A, it's on regular expressions. I'm always surprised, how many of you have used Linux or Unix and regular expressions in those contexts? You guys know how to use a terminal? You guys know what a GUI is, a terminal, right? Okay, so like when you go to the terminal and you type ls star .pdf, what will this do?
We'll list all the PDF files in that directory.
Exactly. What does the star part of the regular of this do?
Any character or literal.
Exactly. Yeah. So this star here is like is a symbol that represents possibly any kind of string. Anything can really go there. And Unix has regular expressions. They're called regex, right? But there's all kinds of like operations on Unix regular expressions. The term the regular part of the regular expression actually comes from the regular languages. So we're going to talk today about regular expressions, which are not exactly the same thing as regular expressions in Unix. And in fact, the regular expressions we're going to talk about today predate those. There are only three operations in the classic regular expressions. They kept adding a bunch of stuff to the Unix things to make it more useful. So it may not be regular anymore, but it's a totally different thing, it turns out, but it comes from basically this, right? A regular expression is simply a description of a regular language. It is a single string that defines an entire regular language. It's a way to define such things, right? So we will give first the definition of a regular expression in the context of this class, and then we'll give several examples and so on and talk about them. Now, unlike the NFA, where I could pretend it's some general model, and then, oh, let's compare it with DFA, and oh, it accidentally happened to be equal to it. I can't do that for the regular expressions because they're literally called regular expressions. So you know that they're already equivalent to the regular languages. So we will prove then the regular expressions are just exactly and only the regular languages, right? So what is a regular expression, first of all? So we have an inductive definition. We have some base cases. The following are regular expressions: the empty string, the empty set, and single symbols. Let's just, for simplicity, assume that that sigma is AB, right? So the empty string, the empty set, A and B are all distinct regular expressions. So there's two parts. There's a syntax and there's a semantics. Right now we're just simply defining the symbols of a regular expression, and then we'll talk about what the regular expression describes, right? And of course, we're going to have an inductive definition. So if Ri, Rj are regular expressions, then so are Ri union Rj, Ri dot Rj, which is a concatenation, and then Ri star. Now, the three operations are union, concatenation, and star, the clean star. By the way, this is named after Stephen Cole Clean. He pronounced his name as Clean. No, he pronounced his name as Claney. His son and his grandfather pronounced his name as Clean, so he was the only one who used that pronunciation of it, but we named many things after it, including the clean star operation, which happens to be the same star as we'll see in Unix in a second. Now, these are just the descriptions of the regular expressions. But what do the regular expressions describe? You can think of a regular expression as just a shorthand way to describe a regular language, right? But which language do they describe? So we let this L operation of R be the language, not the description of the language itself, which could perhaps be an infinite set of strings, right? We have ways to describe infinite sets of strings already. We can use set builder notation, right? W's and sigma star, such that some things happen, right? This itself is a kind of description, if you think about it. That is a string to describe an infinite set of strings. So a regular expression is really a string, but we're going to interchange sometimes the description of the language with the language itself, right? So here's the way you build it up. What the language of the empty set regular expression is simply going to be not exactly the empty string, but it will be a set containing the empty string, right? So this L operation is the language described by the regular expression. If you had to guess, what is L of empty set?
Just an empty set?
Yeah. I'll write it like this. And similarly, L of A and L of B are not exactly just A's and B's, but the set containing A and the set containing B, right? So those are the languages described by our base cases. Now, what about our inductive definitions? Well, the language described by a regular expression, which could be a union, is equal to the union of the languages described by each. Okay. Be forewarned, there are two uses of the same symbol here, which is going to be, make sure you know how to split the hairs. This is a literal symbol. This is an operation on sets. So the regular expression, when we write the union here, it literally contains this character. But writing that character is equivalent to saying I'm going to union both of those languages. So this is a literal operation on sets. And then this is a symbol saying I'm unioning those. That's the difference between the plus symbol on the calculator and the actual addition of the two numbers, right? There's a slight difference between those two. But it's about description versus the actual object that's being described. Concatenation, L of Ri concatenated with Rj is going to be equal to the concatenations of the languages described by those two. Now, what is a concatenation of a language? We use kind of a multiplicative notation, which is like, we just kind of like don't write a symbol. Sometimes you can write a dot or like a little circle or something. But what it means is like, if Li and Lj are languages, let's do A comma B are languages. We define AB to be strings of the form AB such that A is an A and B is an B. You don't get to choose which A is an A and which B is an B. The concatenation is kind of like a Cartesian product. You take every possible string in here and you append it with every possible string in here, and then that's your new language. Okay. And then finally, L of Ri star is going to be the clean star of L of Ri. Now, what is the star of a language? This accounts to 0 or more copies of the language concatenated with itself. So this is going to be L0, union L1, union LL, union, which is in fact just the union of I equals 0 to infinity of L to the I, where L to the I is I copies with itself, right? So right now we don't have any examples. We're just working with just the definition. Are there any questions on just the definition? Okay, we're going to go through some examples. I'm going to give you a regular expression, and then I want you to tell me which language is described by this regular expression, right? Okay. A star. Yeah.
All strings of A, where they're like A, AA, AAA.
What's the shortest string in this language? You're right, there's a couple strings in there.
The empty set?
The empty string, in fact.
The
Yes.
empty string.
Yes. You can have 0 number of A's. 1 A, 2 A's, 3 A's, and so on, right? So think of the star like a placeholder for a number. And then for any possible number that could go there, that's what the language is described by it, right? 0, 1, 2, and so on. By the way, when you star something, it should always contain the empty string, because anything with 0 copies of itself will end up containing the empty string. So this will always be the empty string for any, the set containing the empty string, excuse me, for any possible language. What about A star, B star?
A, or empty string, like, and then A, B. Also,
Give me a characterization of like all the strings in this language. Maybe even those that are not in this language.
all multiples of A and B concat.
Yeah, but more precisely, what about the A's and the B's?
A has to come before B.
Yeah, every A in that string has to come before every B, right? There can never be, so AB, AAA, BB, AA, B, what else? A, B, 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 right? There's no restriction on how many A's or how many B's, but every A has to come before every B, right? What would you describe is its complement? Don't give me a regular expression for the complement, because complement is not a regular operation, as we'll see. But it's only union, concatenation, and star. There is no complement operation here. But what would be a way to complement, to describe the complement? Yeah.
Switch the A and the B.
Yeah. In fact, the complement, the string is definitely not described by this if it contains BA as a substring, right? If there's some B before an A, it's over. Okay. What about A union B?
All strings containing only A's, union, all strings containing only B's.
It's simpler than that. Notice there's no stars. Yeah.
Is it just AB then?
Just AB, yeah. Why? To give you, it's really the union of this, right? According to our inductive definition. Okay? What about A union B star?
Strings containing either A or B.
Yeah. Which strings are those?
And they can be of any length. So that
Okay.
would just be,
Strings of any length containing A's and B's.
So you start with the empty set, then you can have A or B, and then you can have AA, AB, BA, or BB.
Okay.
And
It would be the empty string, but what language is that?
Is that just the language of all possible valid permutations of A and B?
Yeah, which is just all strings.
Yeah.
So it's actually every single string, right? So this, in fact, is another name. What is this one?
Clean something.
Yeah, it's going to be sigma star, right? When we say sigma star, that's the notation we introduce for all strings. And in fact, it's the other way around. This is not the definition of sigma star, of all strings. This is actually just a regular expression, where we use sigma as a shorthand. So in fact, that was a regular expression for all strings, right? What about A star, B, A star? Yeah. Sorry, go ahead.
Any number of A's, a B, and then any number of A's.
That's correct. But give me another way to explain that. That is exactly what it says in a literal sense, but there's another human definition of that. Those strings happen to also be what?
They all have only one B and
Yeah. These are also strings that happen to contain exactly one B, right? Here's how it works. You non-deterministically choose the B, and then you build the A's around it, right? There's no reason that this number of A's has to equal this number of A's or anything. And it is true that some number of A's, a B, and then some number of A's. But another way to say that is these are strings with at least one A in them, right? Not at least one, exactly one, sorry. Okay. What about A union B star? B, A union B star.
Strings containing at least one B.
At least one B. The difference between these two is that here a B is fixed, but no B's can appear before or after it. So this is exactly one B. Not 0 B's and not 2 B's, but exactly one. Here, a B must be fixed somewhere in the string, but some prefix of it can be non-deterministically chosen, some suffix of it can be non-deterministically chosen, and that can include a certain number of B's. Who knows, right? But every string must have at least one B. What about A star, B, A union B star? Yeah.
All strings that start with A, 0 or 1A, and then 1B, and then any other string in the language.
Right, but what's another human explanation for it? That's the literal program, that's literally what it does say, but give me another explanation for such a thing. Yeah.
All strings with all A's until the first B, and then
In the similar of the previous two examples, what's the difference between them? How many B's are in such a, described by such a language, by such a regular expression?
at least 1B,
Yeah. Anything else about it?
and
I'll tell you, it's a trick question because this language happens to be exactly the same one as this one. Right? Those are in fact the same. Those are equal. Kind of why. Here, this non-deterministically chooses any B, and then chooses A's and B's before it and A's and B's after it. Here, what this really does here is non-deterministically choose the first B. Then, of course, it's because it's the first B. Only A's can come before it, and then anything can come after it. So these will describe the same strings, but they may do so in a different way and perhaps even a different order. And the way to think about a regular expression is as two ways. First off, it's a shorthand notation for a regular language. Like it's a simple programming language that describes or enumerates a regular language. But unlike an automaton, it doesn't take input and output. It doesn't say yes and no. The regular expression does not really, there's no input. Where do you put the input? There's no output. Where do you take the output? It somehow only exactly describes the correct strings, right? There's no way even to obviously say a string is not described by a regular expression. So it only somehow positively describes the right strings, you know? So complementing with a regular expression is quite difficult. That's kind of analogous because you can easily take the complement of a DFA by flipping the states. You can't easily take the complement of an NFA because flipping the states does not flip the language, right? So I'll give you an analogy. Let's prove, for example, that A union B describes a certain string of 1, 3, right? So what you can think of a regular expression is that it is not a string, but like a superposition string, where under a sequence of non-deterministic choices, it promises to be a single string in the language. And it can be any string in the language under those non-deterministic choices. So first one you can think about is you non-deterministically choose star, which would be the number of times you concatenate it with itself. So let's say you did it 3 times. Okay, so that's the first non-deterministic choice being made, is the number of times you concatenated. Then for each of these, you think of this as you concatenate this with this with this, but this is the first symbol, this is the second symbol, and this is the third symbol. But no choice has been made about those yet. So you non-deterministically choose A or B for the first symbol, you non-deterministically choose A or B for the second symbol, and then you non-deterministically choose A or B for the third symbol. So if we're given that one, let's say we made 3 non-deterministic choices here, then you could have this go to, let's say, A, B, B. Something like that, right? So it's like a superposition string, that has not made its decisions yet, and then under certain non-deterministic choices, it's a single string in the language. That's another way to view a regular expression. It's like a higher power string that's undetermined. And then when you measure it, it collapses back down, and then you have something real. Questions on these examples of regular expressions so far? Okay, let's do a couple more. What about sigma, sigma star? And we may use sigma as a shorthand for A union B, right? Give me a characterization of those strings.
Same as before, just two of them. So all strings of length two.
It's, so you said it's all strings of length 2? That's,
Actually, if it's,
sorry, go
if
ahead.
it's equal to the, oh, because
No, you're close, you're close.
they said two for the, so,
Let's break it up into parts. What is sigma, sigma, first off?
A union B, A union B.
Yeah. So let's expand A union B, A union B. What is A union B concatenated with A union B? Yeah.
Is it I mean, it's the same language twice. I'm not sure how to phrase it, how you're getting that, but wouldn't it just be the same as sigma star?
Not quite, as we'll see in a second. Oh, yes?
It's all string with odd length, isn't it?
Not odd length, in fact, the opposite. even length.
Even length,
Yes.
sorry, that's what I mean.
Yes.
What you're trying to write is A, B, you know, all that.
Yes. Yes,
So sigma doesn't contain the empty set which you wrote.
exactly. Sigma does not contain the empty set, but sigma star is a subset of, the empty set is a subset of sigma star, but not an element of, right? So sigma star is all possible strings. But here we do not sigma star, but sigma, sigma star, which it turns out is different than, well, let's finish this one and we'll talk about why it's almost, but not exactly sigma star, right? So these are all possible strings of length 2, right? That's what sigma sigma is. Sigma sigma is in fact all strings of length 2. Why? Non-deterministically choose a first symbol, non-deterministically choose a second symbol. That's a string of length 2. So we have 0 or more copies, and you can think we kind of have a distributive law. You concatenate something from the first with something from the second. In the first, it could be A or B, in the second, it could be A or B. So you do AA, B, AA, AB, BA, and BB, right? Kind of a foil in some sense. So you get this finite set of size 4. You star it. So 0 or more copies of strings from this language is going to be strings that are just concatenations of this with each other, which will be a string of even length. If you have a string of even length, it could be broken up into these segments of size 2, right? So this, in fact, will be even length strings. Now, what's the difference between this and, say, sigma star, sigma star? What is sigma star, sigma star? Yeah,
That includes the empty set, so
it does.
that would just be equal to sigma star.
Sorry, the empty string. And in fact, the empty string is actually also here. But what is sigma star, sigma star?
It's the entire language and then concatenated with the entire language.
Yes. It's every possible string concatenated with every possible string. But what could that possibly be? Yes. So to be, I think you guys see the idea. It's just going to be, in fact, all strings. If you take every string and you concatenate with every string, in fact, you get every string. Here's another way to think about this. The empty string is in that one, right? So this is like sigma star concatenated with the empty string, union 0, union 1, something like this, right? But if you concatenate the empty string with every string, that's just going to give you back empty string. So in fact, every string that's in here will be in here, right? So every string, no, sorry, the other way. Every string that's in here will in fact be in here. So in fact, this is contained in sigma star is contained in it, so it's just equal to sigma star. Yeah. That's slightly different than here. Yes?
So is that just like similar to how infinity times infinity is like a
It
bigger
depends who you
infinity?
ask, and you gotta be careful. It's,
Still,
sorry, go ahead.
I was just gonna say it's infinity times infinity, which is a bigger infinity. For our purposes, it's still infinity.
It's closer to thinking about like if you were to pair up every possible real number with every possible real number, you would get like the real numbers back, right? If you take a product of every possible combination of real numbers, you get the real number. Now the size of this, of course, is infinite, but it's still just the same numbers. It's the fact that pairing up strings this way doesn't really do anything, because every string is, of course, a concatenation of any two other strings. So same thing with numbers. It's like one is in there, so you product it, right? Okay, here's one that I don't think anyone is going to get. What is A star concatenated with the empty set? Yeah.
Is it just A star?
No. I knew I'd get someone. What's the other option?
The empty set?
Yeah. Why?
Because if the empty set is no characters, then no characters and no character, or and any character is no characters.
Yeah, so like vacuously, this is a for all statement. The concatenation of languages A and B is such that A is in A and B is in B, but it's for all B and B and for all A and A. So when there is nothing to for all, then vacuously this ends up being empty. It's not something particularly important. You'll never see this as kind of a useless thing, but that's just the way the definition works out. But what about A star empty set, empty string? Yeah. What about, now here's the last trick question. Zero, the empty set star. Yeah,
The empty set?
not quite. It's another one of those tricks.
Got me.
The empty string.
It's in fact the empty string. Why is it the empty string?
Type difference.
Kind of, basically. It's like 0 or more copies of strings in this language, right? So in fact, all the other powers will be, if you take star as 0 or more copies of strings in that language, you're gonna have L to the 0, which is in fact gonna contain the empty string. So this is going to be, in fact, will be the empty set to the 0, union the empty set, union the empty set squared, union. These are all gonna be the empty set, but this one specifically will be the set containing the empty string. 0 or more copies of strings in that language. Doesn't matter if there's no strings in that language. It's just going to be 0 copies of that, which will be the empty string. Now, these two, not important. You know them. Nobody cares. It's not very, it's not a big deal, you know. We care about interesting, positive constructions and not this edge case thing. But I want to remark that we kind of have some algebraic laws, if you think about it, right? The empty set and the empty string appear to act in an interesting way, right? For any regular expression R, what is R with the empty set?
The empty set?
Yeah, okay. What is R union the empty set?
R?
Yeah. What is R concatenated with the empty string?
R?
And what is R union the empty string? This was a trick question.
It depends on whether or not R has the empty string or not.
Yeah, it could be R. It could be R union the empty string if R was not there. But it's just that. That's just the shortest way to explain that one, right? Analogously, what does this remind you of?
Multiplication and addition with 0 and 1.
Exactly. So like for any number n, we have x times 0 is equal to 0, x plus 0 is equal to x, x times 1 is equal to x, and then x plus 1 is equal to, it could be something different, or maybe it's the same in the case it's 0 or something like this, right? So, in fact, it kind of seems like we have like algebraic laws for the way the regular expressions work. In fact, we kind of had PEMDAS, right? What is A union B concatenated with B union C? It's going to look like AB, AC, BB, and BC, right? That's kind of like, what's that called? Foiling, there's a distributive property for it, right? So it appears that there's some kind of like nice name for this thing. It's like algebraic, right? We don't appear to have like inverses or anything like this. This is in fact, you could construct this thing and you could call it, it's called a clean algebra. It's a little difficult to get all the axiomatic laws correctly about what is and isn't a clean algebra. And it took until, I think the problem was posed in like 30s, 40s, no, 50s. And then it took until the 80s for someone to figure out like what actually is a clean algebra. Like what are the laws of the clean algebra? But just know it kind of obeys most of the laws you could probably guess it's going to obey, right? Questions on examples of regular expressions? Yes?
So our union, the set containing the empty string, is basically just R and then the empty string, and if
Exactly.
Okay, got it.
It could maybe not, it's possible that it could be something else or it could be the same thing. For example, our A star union, the empty string, is just A star again, because it already contains the empty string. But A star union, the empty string, what is A star?
1A, at least 1A.
Exactly, so it's 0 or more A's with an A. So this is in fact greater than or equal to 1 A's. But when you union back the empty string, we get 0 A's again. So this is just what?
A star.
Yeah.
Oh, gotcha.
And so on. More questions on just like writing regular expressions. And we're gonna be, regular expressions not only are an interesting way, but they're also a cool shorthand. So if we want to quickly describe a regular expression, like we could do like W's and sigma star, such that W is an odd number of A's or something, right? And then, or we could just throw together a regular expression if it's simple enough, and that's an easy way to write the same thing, right? It's a notation as well as a tool. Questions? Okay. So obviously they're called regular expressions. We need to prove that they are equivalent to the regular languages, right? So we know that there are two objects that also decide regular languages. Those are the DFA and the NFA, right? So what we need to do now is prove, oh, I should not have erased it because that was the definition. That was going to be pretty useful. We need to prove that let L03A be the class of languages which are described by regular expressions. So this is, L is an L03A if there's a regular expression for it. Now it's not the set of regular expressions, but the set of languages described by regular expressions. That's what L03A is. We want to prove this is equivalent to the regular languages. So what we'll do is prove that it's equivalent to either the DFA or the NFA. Which one should we pick, the DFA or the NFA?
NFA?
Why?
Because of the way regular expressions work, it's like a character, a specific character in the string could either be A or B because of the union.
Yeah, it's like non-determinism, basically. Like the regular expressions are non-deterministic. NFAs, by definition, are non-deterministic, so we will just go to the NFA. Now, we could go to the DFA, but the proof will be, because they're equivalent, but the proof will be more cumbersome. So what we'll first prove is that every regular expression has an NFA. Then we'll prove that every NFA has a regular expression. And by doing those two things, we will be sufficient to proving that the regular languages are exactly and only, the regular expressions describe exactly and only the regular languages. So the first one says is that the languages described by regular expressions are not more powerful than the regular languages. And the second one says that every regular language can be described by a regular expression. You combine those two, you get, in fact, that the regular expressions are just equivalent in power to the NFA and the DFA. We've not invented something much more powerful, which we will next time, in fact. So the second, we'll do this first one first. We'll prove that every regular expression has an NFA. Now, the definition, we're not going to work with the actual regular expressions, but in fact, we're going to work with the formal definition of a regular expression. And again, the definition of a regular expression is that it's one of the following. It's the empty set, it's the empty string, it's A or it's B, or if Ri, Rj are regular expressions, and so is Ri union Rj, Ri concatenated with Rj, and then Ri star, right? So given such a recursive definition like this, what proof technique should we use to prove that every regular expression has an NFA? This is a hard question, I think.
Strong induction.
Yeah. Why? Recursion and induction used to mean the same thing, basically. So we have a recursive definition. So we're going to use strong induction. In fact, we're going to use a specific kind of strong induction, which is called structural induction. Okay, you guys remember induction from 2050 vaguely, right? Base cases, inductive hypothesis, inductive step, right? A structural induction is not really a kind of induction, okay? There's this book I have that is called The Handbook of Mathematical Induction. It's 1,000 pages and it contains 800 problems on induction, okay? There are induction problems in geometry, there's induction problems in number theory, in inequalities, in calculus. It has 800 problems in induction. It's great for 2050. I pull problems from there and give it to people. It's a really fun book. It has a single page on structural induction, and it says structural induction. It kind of explains it. It's like it's a technique that's extremely rarely used. It has exactly 2 examples. One of them is in fact this example, which is for regular expressions, and the other example is for the thing in graphs. So it's not really any different than any kind of induction. But what we're going to induct upon is kind of like structurally. What that really means is we're inducting upon something else, which is in fact the number of rules applied to create the number of recursive rules applied to make a regular expression R, right? So when you make a regular expression, in fact, it's like, if you think about it, it's the depth required to construct R in some sense, right? So let's proceed by this quote-unquote structural induction. It's a very rarely used technique, but it's going to be kind of clear. Our base case is going to be what?
The empty set or the empty string? Empty string.
It's going to be, in fact, all of those. So to remark back to structural induction, base cases are like R takes 0 recursive rules. So R has no unions, it has no concatenations, and it has no stars in it. If it takes 0 recursive rules, then R must be one of the following. R must be equal to the empty set. R must be equal to the empty string. R must be equal to A, or R must be equal to B, okay? So why is the empty set regular? Let's prove these 4 base cases. Yeah.
Because it's contained in the language, or it's a single element in the language.
Sure, but like, why is it regular? Like, I guess what I'm asking for is, give me an NFA for this.
Either is it or it isn't.
But what's the actual NFA? Cool thing about proving, by the way, in the whole theory of computation is like, you don't need any complicated mathematics to prove something. You really just need to write programs and have good algorithm design. So to prove something's regular, all of you just give an NFA for it. So give me an NFA that accepts no strings.
Could you just do, you go into a state and then just accept it?
But would that accept some string?
That'll be the empty string. So
Yeah.
would this be just the
I mean,
non-existence?
no transition at all.
And there's a smaller one though, yeah.
The start case is also the accepted case, and then it goes, or you said it's even smaller.
Sorry, that's it.
That's
So yes, start state is the only state which is no accept states. No transitions. Everything implicitly rejects. Everything's done. That's actually the simplest NFA. Everything, I think you guys had a similar idea, right? Yeah, but that is, I mean, it would work to do a different one, but let's just say it's that one. Give me one for the empty string. Give me an NFA that only accepts the empty string. Yeah.
The start state is accept, and if you do any transitions with any symbols, it rejects.
Yes. Cool thing about NFAs is we have implicit reject though. So rather than say if I see anything else I can reject, I can just say that's good enough. Right? That would also work though in a DFA sense. Give me a regular expression for the symbol A that accepts only the single string of length 1, the symbol A.
I have a quick question about NFAs.
Yes.
So the start state is before you accept the letter?
The start state is the state that the computation begins upon. So if the empty string always has a computation in an NFA or even a DFA that begins and ends right there on the start state. As you take transitions, you must take as many transitions as there are length in the word. Epsilons are free, but what possible states you land on in an NFA is the states that are accepted.
Okay.
Yeah. Given a regular expression of just the symbol A, give me an NFA for the symbol A. Yeah.
So the start state and then a transition, and that's the accepted state.
Right. Give me an NFA for the symbol B.
Same thing.
Yep. We have proven that we've proven that these four things are regular. The four base cases are regular. Right? So now we've completed the base case. We agree? So let's now proceed by induction. Suppose, here's our structural inductive hypothesis, Ri and Rj are regular expressions which describe languages decided by NFAs, Ni, and Nj. We give NFAs for Ri union Rj, Ri concatenated with Rj, and then Ri star. Right? Now this proof by induction is in fact highly graphical. Suppose we have an NFA Ni and we have an NFA of Nj. Okay. Okay, something like that. We have two NFAs. How would you construct an NFA for the union of those two?
Just epsilon into each.
Non-deterministically choose which one you want to run on. Okay? Now, there is more that could be said, like in a more formal sense, but the picture is like so obvious it works. Here's the more formal sense. Take all the states, union them together, add a new start state, remove the old two start states, add an epsilon to the old start states, and that's your union. Okay? Some more notation could be involved there, but that picture is pretty clear, right? So we've done this case. Questions on that? Again, these are two NFAs that have regular expressions to define them. So if these two are, this has some regular expression, this is some regular expression. So if you union two regular expressions, you can in fact make an NFA for that bigger regular expression. Right, assuming those two. So that's our induction hypothesis, proves the inductive step for that case. Done. Questions on that? Okay, let's do concatenation and star. So let's do concatenation. I'm in this, okay? Let this be Ni. Let this be Nj. Give me a, how would I combine these to could create a larger NFA for the concatenation. Yes?
Take all accepted states, bridge them epsilon to the start state of nj.
Mm-hmm. There's some more that needs to be done though.
Consider all the reach.
Not quite. Not, that's for determinifying it. It's boring stuff. It's not particularly important yet.
Would it be the start state epsilon to the start state of nj?
Not quite.
Oh no, we remove the
Yeah.
accepting ones.
We just get rid of that. We just get rid of that. Yeah. Then we also make sure that this is not a start state anymore. Okay? So if I were to write out the proof, let's pretend I'm writing a paragraph here, I would say, make that the start state, remove that as a start state. Epsilon from the accepting states of Ni to the start state of Nj, remove these as the accepting states of Ni. Leave these as the accepting states. Why does this work? What is an accepted string of a language? Let's say X is accepted by L of Ni, and then Y is accepted by L of Nj, right? All an accepted string really is a path in a graph. If you think about it, it's an answer that tells you how to get to an accept state, right? So the string is just telling you how a path in the graph, and it's accepted if it's one that tells you how to get to an accept state, right? So if X is a path from here to here, and Y is a path from here to here, then certainly XY will be a path concatenated by these two. Just by definition. But in the construction of this, it's going to go from there to there to there to there, right? So you concatenate the paths together to concatenate the whole thing. And that's kind of like actually how most graph algorithms work. It's the fact that if you take two paths and you join them together, assuming the end of the first one is the start of the second one, you can make a bigger path. Most graph algorithms kind of rely on that property, that joining stuff together is a bigger thing. Combinations of paths can be a bigger path. Okay, that's concatenation. So we've done concatenation. Now what about star? Suppose again we have an NFA, and this one's tricky. What should I do to make this NFA accept a star? Yes?
Have you epsilon all the accepting state back to the start one?
That almost works, but there's a small bug. That creates a bug. It's a slightly more complicated thing, it turns out. I had to look it up to remember exactly what to fix it, but I remember there's a bug when you do that. That's almost correctly, though. Why does that almost work? He's saying epsilon these back to here. The reason that works is because you go to here, you reset, right? 0 more copies, but there's a small problem with that. Yeah.
If there's 0 copies, it doesn't accept it. So
You need to make sure that the empty string is also accepted. And there are cases where that can accept strings it's not supposed to. So what you actually do is you add a new start state. You epsilon to the old start state. You epsilon from all the old start states back to the old start state. And which one do you make accepting? This one. That fixes the slight bug, turns out. Okay, so we've proven that. We've proven it by induction, assuming our inductive hypothesis that Ni and Nj are NFAs that describe languages, decide languages described by Ri and Rj. We give NFAs for languages described by Ri union Rj, Ri concatenate with Rj, and Ra star. Yes?
Why do we need the new state?
Because it could be the case that if you just epsilon here, it doesn't accept the empty string. But the empty string is always a part of the union, the star.
If you do that epsilon just without the new state, couldn't you make that original state the start state and then just
Make it accepting?
Yeah.
Well, what if the problem is, what if there's let's say you bring it in, and what if if you make that accepting, what if there was a self loop here? You might accept a string you didn't anticipate to. Something like this. It's an easy exercise, but at least we can just say that definitely works, even if I don't know why the other thing doesn't work. The simpler thing doesn't work. Yeah. Okay. Two things about this proof. Any questions about the proof before we start commenting on it again.
This is more of a question about the homework.
Mm-hmm.
For the proofs on the homework, I'm assuming that we are not writing graphs, or would writing the graphs be the proofs?
Yes, so if you look at the notes, I have both the pictures and the words. And the correct proof, which should be in fact everything that I said out loud, but didn't write down. That should be included in the proof. But a visual aid like this is very useful, very, very important. Yeah. In the theory of regular languages, and in fact this whole class, it's cool that you don't need a lot of advanced math to prove the theorems. You just need kind of a goofiness. You need like algorithms, like sometimes a proof will be like, oh, we can BFS. Or you need a construction, right? If you think about it, we converted NFAs to DFAs. That was just a construction. That was like building the actual DFA. Here we kind of do the same thing. In fact, not only is this is quote unquote a proof by induction, but it is also kind of an algorithm because it tells you how to convert a regular expression into an NFA. Let's do that example real quick. Suppose we have the regular expression A, B, union, I don't know, BA, star, okay? We can actually apply this inductiveness, this inductive steps to give a regular expression, an NFA for that. That's a regular expression, we can convert it to an NFA. Here's what we're gonna do. First, we're gonna go internally and do our base cases. So we have A, B, and then we have BA. So it's gonna look like this. Okay. Why am I putting the epsilon there when I could have just done A, B? Why am I doing 3 transitions and 4 states when I could have done 3 states and 2 transitions? Because that's what the formal definition calls for. If you take shortcuts, sometimes you can make mistakes, and there are cases where you can like try to simplify something too fast and actually accept something you didn't intend to, right? So now we're gonna take the union of those. So what I'm gonna do is throw the new start state on there and union to the old start states. Now I'm going to take the star of that. And what the star of that entails is that we go back to the old start state with epsilons, add a new start state though, and make that accepting. Okay, so that is an NFA for this regular expression given the construction itself. Right? So in fact, this tells you how to convert an NFA, a regular expression to an NFA. Done. What else? Questions on that? Now, I'm not going to give you a regular expression and say convert this to an NFA. That's not the point of it. By induction, the point is that every regular expression has an NFA. But it's kind of cool that it actually gives you a process to convert the NFA to a regular expression. Right? Questions on that? Second comment on this proof. This actually proves, once we finish that the regular expressions correspond exactly to the regular languages, is that any class of languages with certain properties must contain the regular languages. And in fact, the regular languages are the smallest class. Here's the next theorem. The regular languages are the smallest class. Instead of the base cases, sometimes people say containing all finite languages. And closed under union, concatenation, and star. What this means is if C is any class, so C is containing some set of strings, right? Maybe perhaps C is equal to some hypothetical automaton, something like this, right? We know then that the regular expressions, if C is closed on these operations, then it must contain the regular languages, something like this, right? So the regular languages are in fact the smallest class with these 3 properties. And in fact, those characterize the regular languages as well. If you have anything bigger, that happens to also be closed under union, concatenation, and star and contains finite languages, then necessarily by this inductive proof it must also contain the regular languages. Right? That's not particularly important, but it's kind of an interesting property that the regular languages are the simply described thing, right? Algebraic definition, in fact, right? Any questions on that? Okay, let's go on to the next part. Now we're going to convert a NFA. We're going to go the other way. Let's convert an NFA into a regular expression. Now, this is a little difficult, right? We are going to do this part now. Every regular expression has an NFA, fine. It would be great if we could just go backwards, but it's not necessarily the case that every NFA can be turned into a regular expression. Excuse me, that the process is invertible in some sense. So what we're going to do is just give a regular expression for every NFA. The proof idea is that a regular expression describes something. So what we'll do is, for NFA n, make regex to describe strings that take the NFA from the start to the accept. So the regular expression is going to describe the strings that go from the start state. And again, a string in an NFA is a path in a graph. So this is a description of the correct quote-unquote paths. The regular expression is going to tell you which strings will take you in the NFA from the start to the accept state. So to do so, there's in fact two proofs. One, a messy proof by induction. I'll put it on the homework. The second one is a construction. So we're in fact going to just tell you how to convert an NFA into a regular expression using something called the method of ripping. So we in fact introduce another kind of automaton called a GNFA, which is a generalized NFA. And it has the following properties. Every transition has a regex on it. So in an NFA, every transition is either the empty string, an A or a B, right? Here, we allow an entire regular expression to be on a transition. Well, effectively, what that means is you can have something that looks like this, right? What that basically does is you take that transition if you can match the regular expression to some prefix of the string, non-deterministically, right? The start state has no incoming arrows. The single accept state has no outgoing. And every pair of states has a regex transition. So in fact, in the NFA, if you had no possible transition between them, what you would do then is create a transition with the empty set. So that's a quote-unquote transition, but it defines how to go from one to the other. Right? So this is a GNFA. We're going to first convert the NFA to a GNFA. Then we're going to slowly convert the GNFA into a regular expression. Now, why does this matter is because the method of ripping is we're going to slowly delete states from the GNFA until we're left with one single transition. So we're going to go from something complicated, okay, to a single thing with perhaps a long regular expression on that. So as we repeatedly delete states from our GNFA, we're going to be left with a single transition, and that's going to be our regular expression, right? So here's the way that the method of ripping works. Suppose we have the following substructure, this fragment of an NFA, right? okay? And let's say we have kinds of paths, lots of paths going through there. We want to eliminate this state, it's marked for death. We will then simplify our NFA and have something like this. Those are R1, R2, and R3, and R4 are regular expressions, and we want to delete it, but keep the possible paths in there. So we'll have one path from here to here. What possible transitions, we need to have this one transition. What regular expression should go here? Yes?
R4.
R4, that is one path definitely to go from this state to that state, but there's more than one, in fact. It's going to be something union R4.
R1 concatenated with R3 union R4.
Yes, but that's not the only one as well. There's another one. R2 has a self loop there. So what should it be?
R1, R2 star, R3 union R4.
Yes. So when we rip a state out, we consider all possible paths through that state, and then we update all the remaining transitions, right? So we delete that state, and we're left with a transition at the following. Now, by the way, this is going to explode the length of the regular expression. The regular expression is going to be like really long, but if you repeatedly do this, you're going to be left with a single transition with a regular expression on it, right? Now, here's an open-ended question. Does this remind you of anything from graph algorithms? This is a hard question, but
It feels like people optimization in compilers, but I don't know anything more.
I'll tell you, basically, the history of this thing is like, Clean came up with this method first. Bobby Floyd saw this and was like, actually, I can use that to compute the all pairs shortest path problem. So all pairs shortest path, this is a slight tangent. All pairs shortest path is, can you determine for every possible pair of nodes, the shortest distance between those two nodes, including in the case that there's negative edge weights. And what he came up with was this recurrence, which is like for all I, for all j, and these are for loops for all k, you update the distance between nodes I and j. This is a total tangent, you don't even have to write this down. To be the min of the distance of I, k plus k, k, j, with the min of that with dist I, j, right? So maybe you can see some similarities there. Dist ik is just this is dist ij already as it's been stored. Then this is for all k, dist ik plus dist kj, right? So that's kind of the way you compute all possible pairs to the shortest path between those. You repeatedly do this three for loops like this. Sometimes it's called the V3 algorithm for this reason, because it takes V cubed time. You do this, you're left with a 2D matrix of i's and j's, and then that contains the shortest path. He got this idea by looking at this, right? In fact, this computes what strings will take you from the start to the accept, but on the way it actually computes the shortest paths among everything. Not the shortest paths, the paths. And Bobby Floyd was like, this is the Floyd-Warshall algorithm. He's like, I can actually just use that to compute the shortest path. Instead of taking the union, we take the min, because one of those will be shorter. We don't need to take R2 star, because that's probably going to be something longer, right? So everything is just kind of algorithms back in the day. Right? Now, instead of rigorously proving that this works, let's just do an example. It should be good enough. So let's suppose we have an NFA of the form, let's do a self loop of b's, Let's read an A transition, and then we'll have a self loop of A comma B. And let's make this one accepting. Okay. So first thing we're gonna do is we need to make sure that the start state has no incoming and the accept state has no outgoing. So what we're gonna do is actually add two new states. Make this the new start state. We're gonna epsilon to the old states. By the way, how can you make it so that any NFA has exactly one accept state?
Epsilon all the accepting states to one singular accepting state.
Yeah, if I were to draw that, it would look like. What you do is you add a new accept state. And you epsilon to that. So you can modify any NFA to have exactly one accept state, right? So you, in that case, you may have to do that as well. Now pick a state. This state or this state? Doesn't matter, just pick one. Second one. Let's kill that one. Okay. Now what we're gonna do is replace all possible paths in that one with a regular expression that represents that. So in fact, we'll have this state the same. We'll epsilon to this state. This will still have a self-loop of B. Well, this state will be the same, but now we're gonna have a regular expression here that represents all possible paths from the second state to the fourth state, right? What will that regular expression be?
A concatenation,
Yeah,
A union B star.
correct. Right, this is A or B, so we just do A union B. And then this empty string, let's just put it there so we can have, just to say we did, right? It simplifies out, obviously, but let's just leave it there for now. One more state to delete is that one. So we're gonna be left with this. What is our regular expression gonna be here?
B star A union B star.
Yes, B star, and then whatever this thing is. Okay, so then we're left with our regular expression, which is, if we simplify this as B star, A union B star. Done. In fact, you probably could have come up with this regular expression by just looking at the NFA at the beginning, right? Now, I chose a simple NFA because, in fact, this can get really ugly and really complicated. For example, if you have something like this, if you happen to mark that one for death, unfortunately, you need to incur like a lot of paths. So when you work it out, it'll be something like this. Or for example, this edge would be if you went here, 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 right? Here, 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 and here, right? So there can be quite a large blow up when you delete states. It can get quite ugly. Either way, you leave the computer to do it. In practice, you're never gonna like convert an NFA to a regular expression, but it just shows you that it's possible. The regular expression describes the strings that go from the start to the accept state. This correctness property allows you to repeatedly delete states until you're just left with the correct regular expression. Right. Questions on the GNFA? Okay, we have sufficiently proved that every regular language, every NFA has a regular expression to describe the strings that the NFA would decide. Done. Questions? All right, let's take a break.